Thank you for the invitation. We just talked about it's actually a little bit back to some of my roots. I lived in Lausanne for 1 year in 2001. Did my social service sent from Germany here in a little city, Savigny, just outside here. So it's really nice to be back and have the chance to reflect on something that happened in the time in between. Because after Lausanne, I went to Stuttgart and started my civil engineering studies. Very soon got interested in the work of Frei Otto, being very present at that university, and had the chance to already work as a student in the office SL Rush, where Bodo Rasch has developed in the last over 25 years many very renowned lightweight structures, predominantly in the Middle East. We then founded our own engineering department inside Bodo Rasch's office, and that then later became Structure as an independent engineering firm. And there was a time in between where, as you mentioned, I was at the University of Stuttgart doing a PhD, so I was very much kind of embraced by this whole world of civil engineering and architecture in the dialogue, which is very present in Stuttgart. So I'm going to reflect a little bit about some projects I was involved in, partially in practice from the time working with Bodo Rasch, some parts from the research work I was involved in at university, and then again projects which we were working on very recently in our engineering practice. And I'm going to divide it up a little bit into different ways that we approached the projects. Not so much in a chronological way, but much more in the way we approach the first design ideas and the way we try to develop an engineering system out of an initial design intention, and then let that become a structural system with some degree of efficiency. So the first family of structures I want to talk about is very much related actually to the work that the IL and the team around Frei Otto was pushing as of the late 60s and was publishing in their many IL publications, which was often very much driven by a structural idea and how the physics of the problem can become form, and how that form then dictates the entire design of the system. The first big project I was involved in at Bodo Rasch's office was the structural design of these famous Medina umbrellas. And we were one small unit as structural engineers in a very big design team, all working together on making this mechanical system work in an architectural context set in Saudi Arabia, having it work as a machine because it's a folding kinematic system, having it work structurally in the extremely high winds, and kind of going into a dialogue where there was parts of it very mechanical, designing the kinematics of the system. Other parts were heavily dealing with computation, where we tried to understand the real physics of the problem, as we were forced to design a system at a very high efficiency with very slender cross-sections. Because if you try to build a structure that's kinematic and folding, it's not just beautiful and nice to build it light, it's actually something that you have to achieve in order to make a package that can fold to a very small size. Because tube size, as for these cantilever arms, would be something that's very hindering as you're folding it. So what happened here, and this was predominantly the work of my partner Alex Michalski, is we were trying to understand the real physical behavior of the problem that we cannot see in a wind tunnel test. Because if we scale these large umbrellas to the size of a 1 to 200 or 1 to 500 even model in a wind tunnel, the 1 millimeter thick membrane in real life becomes 5 millimeter thick in the wind tunnel, because we have to put in the pressure sensors inside the membrane. So we're actually doing something that's totally out of scale in the wind tunnel. And at the same time, as you can see here, the structure is actually moving in the wind, and there's some aeroelastic damping involved, and there's additional dynamic problems which we will not see in a wind tunnel. So in this case, and it's a fairly unique case, we actually need the computational wind tunnel with natural winds coming in and not laminar winds to analyze the structure in its true behavior, to then finally achieve something that is very lightweight and very thin in the cross sections, so we can fold it into a small package. There's obviously many things one can talk about with these systems. I'm just going to focus on one very small part, which actually kind of talks a little bit about this dialogue, where you try to make a very efficient design that's also informed by the structure. So we're going to just focus on the edge of the membrane and see how there's these central arms and there's the large diagonal arms, and you can see how there's always these smaller arms that are attached to these main arms. We call these passive arms because they're not directly connected to the central driving system, and they just passively fold out as the umbrella unfolds. And to do so, they're hinged here, which then means if they're attached to the membrane here, we have to make sure that the normal force that the membrane puts into the end of the arm has to be perfectly directed into this arm, so it finds a local equilibrium here. And if you look carefully, you will notice that the edge of the membrane, the curvature actually changes. So there's a structural information that's not hidden inside the shape of the membrane, but that's actually quite visible. And you can see how the edge cable curvature actually decides on how big the force is in that edge cable, and how this radius is much smaller, which leads to a smaller force. And then this is something that I'm sure all the architecture students here learn a lot about, the force equilibrium, and you can then see when you add up these force vectors how you're perfectly pointing in the direction of the arm. And this is actually something that is very much in the DNA of all this work, that there's an information about the force equilibria that's inherent to this entire structural system, and that becomes visible if you carefully look at the shape of the system. So basically, if you break it down into the theory, you can see how adding up the force vectors at the edge of the membrane, you can dictate its direction. And then by playing with different radii on the edge, you can control where the forces are going. And this is something we cannot hide. And this is something we never wanted to hide, because we were very much enjoying this dialogue between creating a shape that works in terms of a shading system, but also structurally. And there's another aspect which one can talk about where this dialogue is happening, and that's in these ornamentics that are set on this umbrella system. These are not printed ornamentics, these are not applications that were just randomly applied to the system. This is something that's structurally informed in terms of a double or triple material at the center of this cone where there's high stress concentrations. And also here where there's concentrated stresses as the umbrella is folding. Because if you see here, as we're folding the umbrella, we're hoisting it up with these little cables to retract the membrane into the system as it's closing, and that's where we need these reinforcements. So what happened here is that we were discussing the shape of this umbrella and also its appearance in terms of the ornamentics between architects, experts in Arabic calligraphy, and structural engineers together with manufacturers who had to then build this in a double layer material and sewing it. And this is a kind of way and approach to work which happened inside this Bodo Rasch's architecture office, where people were actually sitting together in one place at one table working together, which made this approach possible. And by the way, this is a project in Lausanne, in Ouchy, the Hotel Angleterre, where these 4 umbrellas were built by the same office. In this case, you will not see the difference in edge radii, because the passive arms are perfectly perpendicular to the edge, but it's anyway worth visiting and having a closer look at it. A very recent project, we were approached by an architect who had this idea for a central plaza in a little village Imst in Austria, and he wanted to stop traffic from passing through this center of Imst and make it more into a public space, and they needed a roof system for it. The idea was to make a very large pneumatic cushion with ETFE and these central columns that would hold this kind of lightweight roof system. The biggest challenge doing this in a place like Imst is that we have extremely high snow loads. And if you build a pneumatic cushion, you always have to outbalance the outer snow loads with enough pressure on the inside. In this case, there was 2.7 kilonewton of snow on the membrane, which would have meant extremely high inner pressures to this cushion, which is actually very inefficient to build a structure like that. So we were scratching our heads over finding an alternative system to realize this. First of all, again, we started by equilibrating the geometry through a very basic force principle by designing the floor plan in 4 intersecting spoke wheels. So you can imagine that these are 4 independent circles that meet at their tangents and we aligned the entire inner structural system with the radii of these circles. Very basic principle, which you can then set into a parametric model. And at the same time, these bifurcated masts were also based on a force equilibrium. And so we had started the design by designing a force system, which we could then hand back to the architect, who then designed the structure in itself by simply changing the radii and the heights of the bifurcation points in the system. And we knew whatever we would get back is something that's somewhat structurally informed and will lead to a primary steel structure which should be fairly sound and stable. What you can also see is that in section, the structure is flat on the underside and slightly elevated towards the center. So our idea was that we build a structure that passes through different phases. So we have these ETFE cushions that are additionally supported by a cable net. And then on the inside of the structure, on top of this elevation, we put an additional cable net, so we can allow for controlled collapse of the cushion, and it's still at an angle to the outside and can still drain water to the outside. So we expect this cushion to collapse and sit on this inner cable net. So you can see here a multi-layer system. We have the lower cable net ETFE cushion, that bifurcated inner steel structure, a cable net that carries the high snow loads in winter, and then the ETFE on top and another cable net. So it becomes a kind of hybrid system that goes through different phases. A result of designing the geometry totally based on forces is that at the point where you then have to detail it, you're obviously also looking at a system that doesn't kind of perfectly match in right angles, but that has maybe some very odd geometries that you have to resolve. And rather than seeing this as a problem, we actually defined this as the main challenge of the system, where we wanted to really show that everything is aligned to the tangents and to the flows of forces. So we designed the edge girder in a way that it picked up the resultant directions of the cable net and had an integrated rain gutter system in it, which then drained through the inside of the cushion. We wanted to have no air ducts or water pipes seen on the outside. So that created the next challenge, that the bifurcation points of the central masts, they had to remain hollow so we can run all the tubes through it, which we then realized with these steel cast nodes. Something very interesting is that actually it's fairly inexpensive to build these steel cast node nowadays, because we can 3D print and sand the casting molds for it. And actually the most expensive thing for us was to design a perfect surface of these elements and to design the 3D solid model that then goes into the 3D printer. What happens afterwards is actually fairly standardized steel procedures, and they don't care whether they get 6 different nodes or 6 of the same nodes, because they anyway have to reprint the molds every time. This project was actually just finished a week ago, so these are not even the final pictures. You can see there's still some cables hanging on the edges. It's just some first impressions where you can see how these steel cast nodes set in here. You can wonder how we managed to get that membrane over these bifurcated masts. So there was a lot of also thinking involved in the setup of the system, in the way it was erected. And you can maybe understand here how that edge was aligned with the shape of the membrane. Something that we often aim for, and this is really much the Stuttgart engineering school, is that in the details of the structure, we always try to make things look as minimal and as obvious as possible. So the way we judge our structural systems and the way these are constructed is that we don't want to look at the structure and have our attention drawn to a detail, but we rather want to look at it and have everything seemingly obvious. So you can see that this the steel cast node is actually looks like the most obvious way of bifurcating this steel node, whereas the most standard way would have been a bolted connection with bolts on the outside and stiffener plates, where certainly the eye would have gotten stuck on seeing that bit of technical detail on that structure. Structure has a total span of 35 meters and covers this central plaza now. Something that we were very involved with at the ITKE at the University of Stuttgart is using material behavior as a design driver. So not starting with the design in itself and finding a structural answer to it, that where maybe we can align some forces with an initial design idea and then develop off of that a variation of the initial design, but rather look at material properties as they are and see what can come out of that. One of the first projects that we did like this was the project that the class we called it Bend It, and had a collection of students together with the ITKE of Professor Jan Knippers and Achim Menges, who had just joined the university. Actually, at the time, one of the PhDs was Christopher Robella, who was at the IBOA until very recently. And the idea for the course was that we just gave a whole bunch of students just strips of timber veneer, and we had them play with it and find out how it reacts to bending and what kind of equilibrium shapes we can create from that. We started the design class by visiting Frei Otto's famous Multihalle in Mannheim, and then had the chance to actually visit him in his atelier in Warmbronn, and had a very long discussion about how risky it might be to solely rely on material behavior to create shape. This was quite an eye-opener for us, because for most of us we see Frei Otto's work as very ambitious and in a way maybe risky if you look at the 64-meter span central hall of the Multihalle Mannheim. But he thought at that point that solely relying in defining geometry on material behavior might be risky, and he explained to us how they were considering doing this for Mannheim, but they rather relied on the hanging chain model as a geometry which they perfectly could define and understand. He also mentioned, though, that they did several tests to understand how similar a hanging chain model is to that of the bending line of the elastica, which I'm going to get into in a second. So these were the kind of models that students built, sometimes just out of paper or strips of veneer, to understand how they can create an equilibrium system by intersecting elements, bending them, locking them into each other to create shell-like structures. The problem is that jumping from here, from a simple paper model, which actually shows a very complex behavior, into something that you can draw in a CAD system and define analytically, is a very big challenge. Because the only bit of maths that we have to understand the shape of these so-called elastica curves is fairly complex and only can be applied to 2D problems and mainly only Euler's 4 buckling modes. So we were interested in actually finding systems that behave similar. And from that talk to Frei Otto, we'd understood that there's a similarity between the hanging chain, between the catenary and the bending curve of the elastica. And we built this model of a carbon rod and a bicycle chain. And you can see up to a span to sag ratio of about 30% that they pretty much describe exactly the same parabola. And it's only at a higher rise to span ratio where you then see the hanging chain remaining in that perfect parabola shape, and the elastica curve slowly bulges out. And you can also see at the force deflection diagram how at that 30% is also the moment where the elastica becomes much less efficient as an arch, whilst the catenary remains a very efficient arch system. So there's actually structurally no reason to go beyond this shape in terms of a functioning arch system. So what the students did is they built a whole load of models and tried to analyze them in terms of their behavior to find out what kind of equilibrium systems they could find, and then to translate that into similarity models which they can easily script. Because it would be very complex to script the elastica curve into a parametric model, whilst understanding the basic shape of that parabola. Understanding the rise to span ratios is something that you can easily translate into a spline definition, and then actually show some complexity in the behavior that is precise enough for the initial design of the system, which was then fed as an input model into the actual structural analysis, which would then perfectly define the actual shape of the system. Here simulated in FEM, where the entire erection process was re-simulated. So this then became actually the model that really described the geometry. And that also then, from that central script, was the output for the entire bit of production data. This was the first time this robot was used at the University of Stuttgart. So obviously for the just 2D cutting, one could have used another tool, but as we'd only just gotten the robot, that was the first action it could be showing. And this is then the final design, where you can then see also how the system was structurally informed, because you can understand that at the intersection point of these two arches, the structural height is close to 0. So actually we're building a system that's composed of many, many hinges, which would mean if they were all at the same line, it would collapse. And by shifting the lines of hinges across that surface, it becomes a stable structure. With myself coming from a background of membrane structure, I was very intrigued to find out how we can translate this approach by bending elements and relying on their elastic behavior into a system that also interacts as a hybrid with structural membranes. In this case, we were approached by a person from Western France, near Tours, who had in his backyard an old ruined structure, apparently designed by Leonardo da Vinci, and he wanted a very lightweight structure that doesn't harm the existing walls. So we had this idea that we can build these spring-loaded beams that just jam into the courtyards of the structure without having to bolt them into it, and then add a roof structure to it. The design approach here was that basically we just took all the students, a whole bunch of glass fiber rods, went on site and built one-to-one scale models by just understanding how shapes can be created in this kind of spring-loaded system which jams essentially into this little courtyard. And this is actually also very nicely showing how cheap it is in a way to use this approach of elastic bending to create complex shape, because the shape gets created by the equilibrium of the support reactions and the elastic behavior of these rods. And we were mimicking the membrane with a very simple cable net system to understand what we could build. Coming back to Stuttgart, the students again built many, many models, breaking it down into a kind of system that translates into a rule. The rule at the end was that we had 3 points of support with looped GFRP rods into it, and they were all folded on top of each other to create a structural system. And we then took this information from the model to unroll each of the beams and track the points of their intersection, which could then be translated into a structural model where all the lines of intersection were gradually reconnected by elastic cable elements to re-erect the structure and actually find out its true three-dimensional shape. At the end of that form finding process, a membrane surface is added to the glass fiber rods to then give another force that sits in the system and then additionally deforms the entire structure. So what happened here is that we made an FEM simulation, which at the end of the day became a kind of central information model, because the only bit of 3D modeling that we had that could truly describe the system was based on this FEM model, which actually is a major challenge, because FEM is very good for simulating these systems, but it's not at all a design tool. So the simulation that you just saw is a highly sped up in simulation. The total time for form finding would take up to 2 hours on a computer. So it's not something that you can interact with as a design tool. It's because of this that we actually relied on a lot of model building and then very late go onto the computer. Recently, there's been many developments that made computation of these systems faster, mainly based on particle spring systems, integrated into software like Kangaroo or Springform, and that then make this first approach faster. But still, we will always face the challenge that if we as an engineer pick up this work, we will have to go back to zero to re-simulate the entire process of building the structure, so we understand the internal stresses of the system. We cannot just pick up the geometry of someone who's simulated it maybe in Grasshopper and say, great, I'll take that as my engineering model, because then I don't know what are the forces inside the structure that are a result of the reaction process. So it's in one way, in terms of a system where you're only relying on straight, very easily produced members, and you're creating geometry by bending them, it may be very efficient. On the design side, we're actually still facing quite high inefficiencies in terms of making it an integral and fast design process. So we've been working a lot on recent projects and workshop in speeding up this process, interlinking it more, and making it into a faster iteration loop. These are some images of how we set it up. Some of these rods are almost 40 meters long in total length. So a big challenge is actually getting them through that little entrance into that tiny little courtyard without breaking them. Because the minimum bending radius that we could allow is actually the one that's in its final position, and we had to be very careful to not bend them further as we're erecting the system. The most interesting moment always when you build a membrane structure is when you're pre-stressing the membrane, because without having to measure it, if the membrane is without wrinkles, you know that you've pretty much hit it right. In this case, at least this section of the membrane was really nicely pre-stressed, and we're very happy to see how this rod here actually gets pulled up into the air by the membrane pre-stress. The entire system still faced some challenges around the edges because of the differences in stiffness of kind of standard membrane details in contrast to the very elastic system that we were building it on. You can see that it was eventually composed into a multi-layer system with a solid polyester PVC membrane on top. Then we had these tiny little textile hybrid springs in between that would create a space on the inside of the structure. And then the lower side was clad with a mesh membrane to show the inside of it. And so it became a multi-layer system which generated the appropriate stiffness for the roof. As part of my ongoing research at the ITKE in Stuttgart, we investigated how these bending systems can actually be used for kinematics without hinges. Because if you imagine that all of these structures, which I just showed, solidly rely on their elastic deformation behavior, and you use materials like glass fiber reinforced plastics, which have a very low creep in comparison to timber, you can also imagine that you can use this process of erection as a repetitive process and create a kinematic or adaptive system out of it. The research project was done in a collaboration with biologists from the University of Freiburg and some material scientists from Denkendorf. And the biologists predominantly analyzed plant movements because they knew that a lot of plants, as they open and blossom or even just move their leaves, they all rely on elastic deformation rather than discrete hinges. So we went through a very long phase in the beginning of the project by just scanning plant movements and building very simple initial models to understand the underlying mechanism. The plant that we got stuck on was this one, the Strelitzia reginae, or birds of paradise plant. And that was the very first model that we built, where we saw that if we have these cantilevering little arms and we add a fin to it, that as we're bending down the arm, the fin folds to the side. If you look at the plant itself, you can see how this mechanism is happening. The plant is pollinated by birds in South Africa. And this is actually the landing stem which the bird will land on. And the sheer weight of the bird will bend it down. That opens the leaf and pollinates the bird's foot, who will then land on the next perch. And this is how pollination is controlled in the system. We ran this tests over 3,000 times on the plant and saw that it actually never failed, which the biologists didn't understand because it doesn't make sense for the plant to be that strong because it only blossoms for about 2 weeks. But they later understood that it's actually designed for a much higher weight of lizards who sometimes go on top of the plant rather than it being designed for the small weight of the bird and the multiple loading cycles. This whole breaking down and abstraction of the system was actually a really interesting process for us as engineers, because when we first saw this plant, and especially when the biologists showed us the first scans and sections of the system, we were really excited about what we were seeing, and we were starting to imagine how there must be these tension systems that are in this leaf and maybe some eccentricities in these tension lines which kind of create this mechanism. And interestingly, it actually took us a couple of days to realize just how simple that mechanism is. And you can just simply describe it by something like torsional buckling, where you see if you have a fairly elastic fin and you're bending it, it just buckles to the side because that's much easier for that fin rather than elongating around the top. So it's a kind of torsional buckling mechanism that's underlying it. The interesting lesson learned is then that we as civil engineers were trained to avoid something like this, and so it took a little while to understand that that's actually what the plant is doing and that you can use this as a mechanism in a controlled way. And what we usually learn when we design bridges is that actually when you have 4 hinges in a line as you're reinforcing this bridge with a cable system, that as you load it with weight it will swing to the side, whereas if you have that eccentricity in it, it'll be a stable structure. So this is actually something that we had at our institute and that we teach architects in the first semester. And it took us a while to realize that this is actually what the plant does. And it doesn't have a perfect hinge here, but it has an elastic zone, and that is what creates the mechanism. So in hindsight, when we look at this research in biomimicry, we often find that it's not so much the very specific solution that we find in a natural system which directly translate into a technical answer, but it's more the inspirations that happen on the way and the way that you learn to rethink the way you're educated or the way that you approach to solve a problem. If you look at the detail of the system, you can also imagine that as we're folding this fin that you will find very high notch stresses at this point, which is a question that you can return to biologists because the plant must have solved that problem. And the biologists actually know many answers to how there's elastic large aerial elements connecting to a stiffer linear element, and you find that in every leaf. And there's actually been a lot of work done on understanding the geometry of this leaf by Matek, the so-called tension triangles. And we were very surprised to actually see it applied to our system and how the tension triangles largely reduce the notch stresses on the corner here. You can also see how this is a gradient material setup now in glass fiber reinforced plastic. And so it's a very bespoke material layout to the specific problem and the specific size of this lamella, which then creates this folding mechanism. This is one of the many FEM simulations that we did to understand the ideal material layout for the system, and then some prototypes that were built during the project. These first prototypes were actuated by eccentric pistons that sit on the back and actually a tiny little hinge that sits back here. This project has been ongoing at the ITKE. Very recently there was a bionic exhibition opened in Stuttgart, so anyone who comes to Stuttgart should take the time to visit that, where now they have actuated these systems with pneumatic tubes that sit on the back to actually cancel that last hinge that we still had in our system. So the last section of types of projects I want to talk about is those where this material information and the force information actually come together, sometimes actually only at a very specific detail of a project, but it can maybe show you a little bit how some of these projects, which may be very research-based and sometimes even very far away from practice, the lessons learned from this work can very specifically inform day-to-day problems that we find in practice. Before going into the practical examples, I still want to show you this structure that we built with students last year at the University of Hamburg. In Hamburg, I had the chance to have a student group of 8 architects and 8 engineers that were both joining the same course. And from the projects I'd done in Stuttgart, I'd always understood that it's actually quite a big challenge having a large group of students working on one specific equilibrium system. We always had in our projects in Stuttgart, at the end of the day, it was a team of 1 or 2 students who were solely responsible for the computational model. And then there was a whole bunch of students organized around them who were more involved with material testing or with the organizational parts or the building parts of it. But it often came down to just very few students and individuals who were controlling the design system. And I wanted to face this challenge with the students in Hamburg and set up a way that we can all work together into one information model. Again, we started by building models, just understanding basic equilibrium systems that you can set up between elastically bent glass fiber rods and pre-stressed membranes. Out of these many models, they slowly started designing structural systems which were meant to hang in the main entrance hall of the university. Then we had a little competition, internal competition, and we democratically decided to build one of these suggested systems. And then a large focus of the project was actually setting up a design system where the entire computational information model is based on a cloud. And we set up several expertise groups around that model where we had structural engineers, we had people doing details, people doing the form finding of the system, people doing the whole project management, which were connecting to the system with Excel. So we could all work off of one central information model and not have one single person being responsible for it, but rather the entire group of students. This meant that we had to have a central tree structure that held all the information, and we had to very carefully version our problem. At the end of the day, this meant though that we could actually all work in parallel, and whilst the structural engineers were still optimizing the system in its form finding, the people doing the detail could work on an earlier version of the structure and already parametrically design the details of the system. One central problem again was that of organizing the resultant forces in the system. So this is exactly the same problem that we resolved on the Medina umbrellas, but in a much more 3D problem, because we only had very precise points on the ceiling of the roof and on the sides of the building where we could anchor our system to. So we had to make sure that wherever the cables are going, they're perfectly in the resultant direction of the structural system itself. So part of that optimization was organizing the resultant force directions off of that central model, which then again was informed by multiple material tests. We were hanging the structure of Dyneema ropes, which was the stiffest and lightest that we could get, but still it has some elasticity. And because we could only erect the structure from the side by pulling it from the sides, we had to carefully mark the cables and show exactly how far we have to pull them to find the final geometry. And so we needed that bit of information. At the end of the day, interestingly, again, the main design driver was the fire system. So we connected to one of these connection plates where the sprinkler system is set, and that actually was totally minimizing the amount of force that we could attach to the ceiling. So many design iterations went over changing the angles, changing the size, changing the overall pre-stress in the system until we could reach a system where the maximum load, also with a little bit of wind on it, on the inside of the building, would not exceed the capacity of this connection. Very exciting is when you work with architects and engineers together that you really can define these experts groups. So we went quite far also into material testing to understand the exact elastic behavior of these glass fiber rods. But then again, sadly, and this is also very true to these university problems, you can analyze everything, but at the end of the day, when we ordered the rods, they sent us the wrong ones. So this was a little bit besides the point to do all this testing. But I guess that's also the reality of these kind of projects, which are certainly also present in day-to-day practice. One of the biggest challenge in this entire project again came from the fire rating, because we were in the main entrance hall of this building, and we had to use an A1 class membrane material, which essentially doesn't exist. So all we could use is pure glass fiber without any coating on it, which is a major challenge for a membrane structure because it has essentially no stretch at all. And if you pre-stress a membrane, you actually quite like to have a bit of compensation in it and pull some stress out of it. First of all, so the geometric inaccuracies that you have from the production process and from not perfectly controlling the boundary conditions are overcome by the amount of pre-stress that you put into the system, and then obviously also change in temperature, change in elongation of the cable system would not have such a big impact on the total pre-stress of the structure. So whoever was in Hamburg would have probably also seen that the final system as we build it did not reach that goal of a perfectly wrinkle-free membrane, which was mainly the challenge of the pure glass fiber material. The material was so challenging that the initial company who was going to produce the membrane for us simply refused to manufacture it, because they said you cannot sew this material. But we were so far into the project that we said we have to do it anyway. So we hijacked the model builder from SL Rasch, who came up to Hamburg, and then we sewed the membrane all together with the students. Which actually at the end of the day was a very nice part of the project, to see that the students actually produced the entire systems themselves. The details where the beams are connecting to the central ring are based on this kind of digital detail system, where the off-going angles from that central ring are all individual, and a small group of students faced that challenge. And then came the big day when we set up all these individual cables and started pulling up the system into this larger space of the entrance hall. Here you can see the system as these two rings of these opposing membranes are set at a distance. And the design idea of this team was that they wanted to build two totally independent membrane structures, and they wanted to show how they can control the force equilibrium by having them almost touch each other at these two central rings, them being more or less perfectly parallel, but not at all structurally connected. So this was the bit that we wanted to show, that we can control the forces in the system, so the rings at the end of the day are set perfectly parallel and at the same distance, just by pulling it from the outside to the design point. As I mentioned though, within the membrane system we did face some challenges with making it a perfectly pre-stressed membrane. So this was the gap that we were looking for. When we now design membrane structures in our office, we now actually rely on a lot of this experience that we made in university in these student workshops. And with systems that may look fairly classical as a membrane structure, we're actually using the same approaches, simply to make the design iterations faster and make it possible to work just in the same way how we worked in Bodo Rasch's office, sitting at the same desk with the architects and iterating very fast over different designs. The computational means that we now have in these parametric tools actually make this possible also at a distance to the architect, who may be somewhere totally different in the world, where we can then set up a model that creates both the architectural model and the FEM model. And this gives us the chance to fastly iterate through different design ideas and then set up an efficient system. Let me see how I can start this video. So this is a convertible shading structure here in Switzerland, in Bux, a small town north of Chur. And they have this central shopping road, pedestrian road, Metzergasse, 54 meters span, 12 meters wide, and they wanted a convertible roof in it. The big challenge was that the existing structures are sometimes, some of them are quite old, some of them are newly built. So every point where we were connecting the structure to the building had to be individually designed. And so the design iterations that we had to undergo was mainly optimizing these support reactions here and finding a kind of minimal solution for that. In terms of the kinematics of the system, often when you build a retractable membrane, you divide the problem into several different driving systems. So you have one driving system which can travel fast at a low force, and then at the end you grab the membrane for the final pre-stressing with a different driving system that covers a short distance at a very high force. And this is essentially what makes convertible membrane structures extremely expensive, because of the mechanics involved in it. For this project, we tried to design a system which, or we actually succeeded in designing a system that is solely driven by a single motor drive in the back of the structure, with a cable system that only pulls the front edge of the membrane, and then here is that central driving system that pulls it. And this was possible because we connected the membrane on the sides to sledges that sit on these rails, which have an extremely low friction. And these are actually designed for robots in heavy car industry. And some of these rails are actually designed to be put outside. And because of this extremely low friction that we have on here, it was enough to pull that only the very first corner plate of it and have all the other corner points passively travel along. So in here, this whole game of equilibrating forces and having the resultants perfectly point perpendicular to the rail was obviously a very important aspect, because any force that is at a slight angle to the rail, the sledge will simply pull aside. And if you design it not carefully and the sledge pulls aside, it basically just means that you get big wrinkles in the membrane because it finds a different equilibrium configuration which it was not designed for. Another challenge, and this is what I meant, that sometimes the things that we explore at university come into practice at a very deep, detailed moment, is the way we tensioned the membrane here at the corner plate. Normally you'd get a laser cut plate here and some pulley systems to adjust the length, and maybe some hinges in the back here to control that all the moments are free. And we wanted actually this very pointy corner here, and we're not very happy with the early designs of the system. So what we did is, well, let's actually just build a material spring here. So what we did is we analyzed the elasticity of the belts that we could connect it with. And what was very important here is that the properties of this belt will hugely change as you're sewing it. So we had to run several tests of how to sew this belt in multi-layers wrapped in membrane so it's UV protected, and understand the exact elastic behavior so we could design the length of the belt to become the spring connection and the kind of pre-stressing bit of that corner plate. So that at the end of the day we have these very pointy and only membrane material corners. And this is again what I was mentioning earlier on. As you're walking past this roof now, your eye does not get stuck on a bit of mechanical detailing, but it's something that looks rather obvious, and that is actually what we were particularly aiming for. The last project I want to share is a project which we recently built in the east of Germany, which kind of talks a little bit about the challenges that we meet today, which are an outcome of the design tools that we're using. And we found that because of the means that we have to create complex geometries in our CAD models, to build a grid shell which is totally individual at every node and beam length and the orientations of the nodes, even creating something that goes from 7 nodes here to 6 and sometimes 5 nodes. So everything is different in this grid shell. And we also see that as a structural engineer, once you get a 3D CAD model, it's actually very fast to create a 3D FEM model and analyze the system without realizing what challenges might come in later as we're detailing it. And this is kind of what happened with this project, that it was designed and put into tender, and it was realized that the individual shape of every node and the way this was designed became a challenge for the steel manufacturing. Obviously there's many solutions to design nodes like that, but the initial price idea for this project did not allow for these more sophisticated solutions with milled joints as we usually see them in these grid shells today. So we came into this project with a suggestion that we can break down the node into 2D laser cut steel plates, which we developed together with Arnold Walz from Stuttgart from the Office Design to Production, and basically followed the idea that we have just these swords that sit at the end of the tubes and 2 plates which give the entire different information about the geometry of the system. So you can imagine that you can control the angle of the pipes with the way they're slotted into these head plates, and that you can control the angle of the shell itself by changing the angle of the sword here. And then as you start doing this, you also realize that as we have these steel plates anyway on the laser cutting machine, we can also use the laser to write additional information onto that piece of steel, so that we can at the end of the day totally avoid shop drawings in the entire system, which will then make it a lot cheaper than any other standard system. So what we ended up with is a node that only has 1 bolt, whereas the initial design had steel swords with 8 bolts per connection. We have an enormous structural height at the node, so the overall weight could go down, and we totally avoided shop drawings. And the steel manufacturer did not have to build timber plates which he would slot into the connection to control the way he would weld it. Because the only bit of welding he has to do is at the back here, which is a very simple weld. Another challenge then is the actual laser cutting, because we're now cutting very thick plates up to 25 millimeters, which only works at the precision that we need in these slotted holes with edge cooling. So there's also a process of understanding how this can actually be manufactured to the precision that is needed. And in terms of the engineering and the material behavior of steel in such a connection, we actually faced a totally new challenge as well, because this form-fit steel connection that we have here is something that is not covered by the general design codes that we work with. What is quite nice, though, that the Eurocode allows us to design steel connections based on complex FEM modeling. Part of it says actually that you have to prove that you have modeled complex connections before. And so we could set up these models where we actually simulated very precisely how there is these frictionless contacts in these form-fit connections of these slotted holes. And we could only make it efficient in terms of the plate thickness if we allowed a large amount of plastification of the system under its maximum loads. So in order to not do this for every single connection of the system, which would have meant it would be very inefficient again, we then classified different parts of the structure and found an analytical way to calculate this slotted connection, which could then cover the entire system, and then we would only pick out the maximum utilized nodes to run a complex analysis on. This is where you can see a bit how the system was then translated into a 2D map, where we could classify different force categories, which would then decide on plate thicknesses, and we would always pick the maximum node from one of these classes to simulate precisely. The next challenge then is to actually not just think about its manufacturing, but also think about the erection of the system. So what we did here is we designed the node with a little hole of that cocked connection sticking out, and there's a little temporary pin that's set through here. And the connection was actually designed in a way that the longest beam in a horizontal configuration can freely cantilever off of this plate. This is only possible because it's a perfect form fit of this cocked connection, temporarily held by this little pin, which then made it possible that actually only 2 or 3 people at the time erected that entire system. Because there was one guy organizing the steel parts, the other one shifting it up, and this guy could all by himself connect this entire system. And whenever an entire ring was closed, they set the outside plate on it, and the structure was set in its final position. You can also see here, if you look at some of the points, when you program such a system, you always have to think about the most extreme cases, because there's nothing more frustrating than perfectly programming the round plate and it working for 98% of the structure, and then you're stuck hand designing these positions where the round plate doesn't work anymore. So it still happens that some of the corners cannot be automatically generated, but you will find that you can spend just as much time resolving situations like this than actually resolving the entire system. So this is the steel structure in its final position. You can see here how there's actually some very extreme connections where there's pipes coming from totally different angles into this connection, some from the underside, some from the top side, just as the structure goes into the saddle, and these were the most challenging points to resolve. This is then the final system with the ETFE cushions. All these plates are also individually cut, which then connect to the rain gutter system of the ETFE cushions from the outside. This is some impressions of the finished structure, and at the recent opening at the so-called Saurier Park. So the actual initial design was the idea that these look like large eggs, which lead to a whole set of challenges. So in summary, I want to just bring up the 3 points which were always highlighted at the IL, and these were kind of the lightweight principles that the whole group around Frei Otto, and still today as we are in this practice, follow. And that's looking for light materials, designing light structures, and designing light systems. Systems in the case that we say we are designing integral and not additive. And if you look into nature, we recently published a guideline in the German Engineering Club about biomimetic buildings. And in this guideline, we published these basic approaches that you also find in biology, where you see that a lot of natural systems rely on heterogeneity, on anisotropy in material, on hierarchical systems, multifunctionality, redundancy of systems, and adaptability. And now if you actually put these two side to side, you actually see that what we do and the rules that we follow in lightweight systems are actually seen as ways of that evolution has brought up in nature. So light materials and anisotropic materials are actually something that often go hand in hand. And we see that the structures, as they become light, they often rely on hierarchical systems, and they can be very heterogeneous in the way they resolve problems. And the aspect of light systems often relies on multifunctionality of the system and on its adaptability. This is what I want to conclude with, and I hope that the film of Otto will maybe give you more of an idea of what the Stuttgart thinking of engineering and architecture as a dialogue has brought up in the recent years. Thank you.